What if I told you there's a way to process a never-ending stream of data with constant, predictable speed and with absolutely zero costly data shuffling? Well, that's the superpower of the circular buffer. It's a surprisingly simple data structure that powers some of the most demanding software out there. So let's dive in and see how it works.
I mean, really think about this for a second. You've got data pouring in, maybe it's audio from a microphone, packets from a network, or a ton of sensor readings. You have to handle it in the order it arrived, right? But if you just use a standard list or an array, you're constantly fighting with it. You're making space at the end, and then when you process something from the front, you have to shuffle everything else down. It's just so inefficient. It's a recipe for lag. So how do you get around that?
Okay, so on the left, you can see the problem. This is the naive way. With a regular array, every single time you remove an element from the front, every other element has to shift over. That's what we call an O of N operation, and it means the work grows with the amount of data. It's a huge performance bottleneck. But on the right, you see the promise of the circular buffer. It does the exact same job in constant time. O of 1, no shifting, ever.
The solution is to completely change how we think about memory. We need to stop seeing it as a straight line and instead imagine it as a loop. And that, right there, is the core concept behind the circular buffer, which is sometimes called a ring buffer.
So here's the formal definition. Okay, sounds a little academic, but what does it really mean? It just means you grab one fixed-sized chunk of memory, and you pretend that the very end of that block is magically connected right back to the beginning, making this continuous circle.
You know, the best way to picture this is to think of a conveyor belt in a factory, just going around in a loop. You have a producer, that's one person, putting boxes onto the belt at one spot, and you have a consumer, another person, taking them off somewhere else. The belt itself just keeps on turning. The important thing is the boxes aren't being shuffled around, only the belt moves. This is a perfect analogy for how a circular buffer works.
Okay, so how do we actually create this loop when computer memory is just a straight line? Well, the secret is surprisingly simple. It all comes down to two little pointers that just chase each other around like the hands on a clock. So meet the two main characters in this story, the head pointer and the tail pointer. Think of the head as the read position. It always points to the oldest data, the next thing we're going to read. The tail is the write position. It points to the next empty spot where new data can go. And they both just chase each other in one direction, clockwise. So the first core operation is called enqueue. That's just a fancy word for adding an item. And it's super simple. You just place the new data right where the tail pointer is pointing, and then you just nudge the tail one step forward. That's it. Job done. And the second operation, dequeue, is pretty much the same thing, just on the other side. You read the data from where the head pointer is, and then you advance the head one step forward. This effectively removes the item. But notice what we didn't do. We didn't have to shift any other data at all. And this right here is the single most important thing to remember. If you get one thing from all this, it's this. The data itself is stationary. It's lazy. It doesn't move. Only the lightweight head and tail pointers do all the work. That is the entire source of its incredible efficiency. Okay, but this brilliant design leads to a classic little puzzle. What happens if the head pointer eventually catches up to the tail pointer and they're both pointing at the exact same spot? What does that mean? Has the consumer read all the data, making the buffer empty? Or has the producer filled every single slot, making it completely full? It's ambiguous. You can't tell just by looking at them. So how do we solve this? Well, there are three really popular solutions. First, you could just sacrifice one slot and never use it. It's simple but a little wasteful. Second, you could use a special wrap bit to keep track of how many laps the pointers have made. It's efficient but adds a bit of complexity. Or, and this is my personal favorite just for its pure clarity, you can just keep a separate counter for the size. If the size is 0, it's empty. If size equals capacity, well, then it's full. It's simple and there's absolutely no ambiguity. All right, enough theory for a minute. Let's get our hands dirty, look at the code, and really analyze the performance here. This is it. This is the holy grail. Constant time, O of 1. It doesn't matter if your buffer holds 10 items or 10 million items. Adding an element or removing an element takes the exact same tiny amount of time. And why is it O of 1? Let's just hammer this home. It's because every operation, adding, removing, even just peeking at the next item, is just a couple of simple steps.
You write or read one value, and you do one tiny calculation to move a pointer. There are no loops, there's no data copying, no matter how full the buffer gets. That is pure constant time efficiency.
So how does it stack up against some of the other options out there? Well, a linked list queue is great because it can grow, but it's not very cache-friendly. A resizing array is also flexible, but every once in a while it suffers from these really expensive resizing operations. The circular buffer, though, it wins hands down when you need predictable, blazing fast performance within a known size limit.
So what's the magic that makes the pointers wrap around from the end back to the beginning? It's not magic at all, actually. It's an incredibly simple and fast math operation, the modulo operator. All it does is find the remainder of a division. So if our buffer has a capacity of, say, 6, and our index is at 5, the next index is 5 plus 1 modulo 6. And what's the remainder of 6 divided by 6? It's 0. It elegantly sends that pointer right back to the start, creating our loop.
Now, I want to be clear, this isn't just some academic exercise. This data structure is a total workhorse out there in the real world. You'll find it in systems where performance is absolutely, positively critical. In fact, you interact with circular buffers probably every single day. They're in audio and video players, buffering data to give you smooth playback. They're inside your network card, buffering packets as they fly in. They're fundamental to operating systems for handling input from your keyboard and your mouse. I mean, they're truly the unsung heroes of real-time data processing. And hey, if you're a software engineer, this is absolute gold for technical interviews. If this topic comes up, be ready to talk about the trade-offs. You should be asking clarifying questions like, is the capacity really fixed? How are we going to handle that full versus empty ambiguity? And hey, does this thing need to be thread safe for multiple producers or consumers? Knowing these details shows a much, much deeper level of understanding. So we've seen that the circular buffer's greatest strength, its superpower, is its absolute mastery of a fixed memory space. That's what gives us that predictable, beautiful O of 1 performance. But this leaves us with one final lingering question. How would you take these principles and design a version that could grow on demand? And more importantly, what performance trade-offs would you have to make to get there?